to D. Okay? You're getting close. You're getting real close. Your answer to D should be around 8. Okay? So the only thing that changes on D, you still have the 4 millimoles of your acid. Now you have 3 millimoles of your base. This still starts at 0. Now you go -3, -3, +3. So the only difference on D is that now, on this part over here, that log, you're taking the log of 3/1. Okay? That's it. And now again, recognize this. Don't get lost in the math. Okay? That's why I say AP chemistry is a math class with chemicals. That's all it is. Okay? You're taking the log of 3. When you take the log of 3, is that number bigger or smaller than 1? I'm losing my voice a little bit. I got emotional with it. It's bigger than 1. So your pH is going to be bigger than your pKa value because you're going to add that value to it. Okay? Go with that. Now, here's the most challenging problem on here. And that's E. Okay? So I'm going to take you through E. We're going to work E start to finish. Okay? Start to finish. Now, this is not going to be on the quiz tomorrow in terms of like a neutralization works fully thing. You have to do all this process. This is not a problem like E. Is not going to be on the test tomorrow. Okay? Not going to be. It will be eventually, just not tomorrow. Okay. So you start off with Hockle and OH. You're getting water and aqua, which is just kind of fun to say. So I got 4 millimoles of my acid. I have 4 millimoles of my hydroxide, 0. -4, -4, +4. So right away, bells and whistles should go off. Alarms. Oh, fully neutralized. Okay? Because I have fully consumed all of my acid and all of my base. Okay? So none of that molecular forms exist. Okay? It's gone. It's all been consumed. So now we need to shift our focus over to this side. Okay? So now we're going to start a secondary reaction. Why are we going to start a second reaction between alcohol and the water?
Because it's a strong conjugate base.
Beautiful. Alcohol is the conjugate base off of a weak acid. It's not stable. What's it going to do?
Go back.
It's going to go back to the water and go, hey, spare a proton. Water's going to go, I got you. Okay? So now you start a second chart. You have a second reaction that's going to take place. So your secondary reaction is going to be alcohol plus the water. And what are you going to get out of that reaction?
Alcohol.
You're going to make more alcohol.
OH-.
And what's going to be left over? Oh, now we're going to make hydroxide. Cool. But we run into a couple of problems. Here's my reaction. Here's my problem. There's 2 bits of information that I need to do this. Okay? There's 2 different bits of information. And I don't have either one of them right away. I need the concentration of my alcohol at this point. Not molarity, not moles. I need concentration. Okay? I need concentration. But I know how many millimoles of alcohol I have. So if I know how many millimoles of alcohol that I have, and I know the total volume, what can I do? Divide by the total volume. So you do this, you're going to take, in this case, 4 millimoles, divide that by the total volume of 80 milliliters, and you're going to get the concentration of your alcohol, which in this case is 5.00 times 10 to the minus second. Okay? Everybody see how I got that? You take your total millimoles that are left over of your anion. Divide that by the sum total of everything that's in that beaker, because you need the concentration at that point. Now, the beauty of this is, how much Hockle and OH do you assume that you start with? 0. So this is kind of retro. When you get to E is going to start the same way that you did with A. The only difference is that you're going to start with Hockle and make Hockle. On A, you started with Hockle and you made Hockle. Okay, which sounds like a horrible Dr. Seuss rhyme. So, isn't it awful? Look at the Hockle. Oh my. So, how much of the Hockle are you...
Oh, we're beatboxing over
Oh, stop. Okay. So, how much of the Hockle is going to ionize? No! How about X? How about X? How much are you going to make over here?
Plus A. Plus A.
Old school. Okay? XX. So my Hockle becomes 5.00 times 10 to the minus second minus X. That's going to be X, and that's going to be X. Now, what is Hockle acting as? An acid or a base? Hockle is acting as a base. So what do I need? KD value. Ah, Mr. Chem. Screwed.
No.
Oh, no.
KA,
Water. I mean, 1.00 times 10 14. Ionization.
Do you know what the Ka is?
Yeah. Auto ionization of water.
So you can find the E.
KB. Yeah.
So I can take that Ka value, because times Kb equals the auto ionization constant of water, right? So I can take that divided by my Ka, boom, there's my Kb. So in this situation, my Kb is going to equal whatever you got from this, the 1.00 times 10 to the negative 14, okay? And that's going to equal x squared over 0.05. Okay? Kb is going to be such a small value that the subtraction of that x isn't going to make any difference. Okay? Now, here's the last and final thought process. Listen to me very carefully, because this is notoriously where the wheels fall off. When you get x, what are you getting?
OH concentrations.
You're getting the concentration of hydroxide ion. This is not the hydronium ion. This is the concentration of your hydroxide ion. So when you get X, and we're not after POH, we're after pH, what are you going to do?
14 minus DOH.
14 minus your POH. So your answer to E should be around 10. Okay? So what that means, and this is at this neutralization point. So if you were to draw a graph of pH versus volume, and that graph is going to go like that, that midpoint of that graph, this is why I had you do that Ka lab before we did this, because now the graphs make sense. Okay? So now, when you go to that Ka, that equivalence point, and you come across, the midpoint of that is going to be at about 10. Okay? If this had been a strong acid with hydroxide, that equivalence point would have been lower, and that would have been 7. So if you're given a graph of titrations, and you're trying to figure out if you're graphing a weak acid or a strong acid, look at where the equivalent point is. If the equivalent point of that graph is above 7, promise you, you've titrated a weak acid. If that equivalent point is at 7, you've titrated a strong acid, because there's no secondary reaction to happen. Okay? Cool with that. That's the most complex one. There is not going to be one on the quiz like that tomorrow. But on the third quiz, promise you, there's going to be one. Okay, now when you get to F, do not overcomplicate F. Okay? So on F, here's what you've got. You've got Hochul plus hydroxide yielding water plus alcohol. Now, if you notice on this one, you have 4 millimoles of your acid, but now you have 4.5 millimoles of your strong base. Okay? 0. -4, you have a 0.5 millimole of hydroxide. Now, technically, is the water and the alcohol going to produce some hydroxide ions? Technically, yes. That's like you walking to the ocean and taking a cup of water and pouring it into the ocean. This will generate some hydroxide ions, but it's like pouring a cup of water into the ocean. Did you technically raise the water level of the ocean? Yeah. Enough to worry about? No. This is by far and away the dominant source of your hydroxide ion. Okay? You don't have to go through the whole secondary reaction again because the amount that it's going to make is so minuscule relative to this. So just take your 0.5 millimoles, divide that by the total volume. At that point, that's the concentration of your hydroxide ions. Are you going to get some from the other reaction? Yes. Is it enough to worry about? No. Okay. There's your concentration of your hydroxide ions. Take the negative log of that. What are you going to get? Your pOH. So your answer to F should be around 12. Okay? Got it. Okay. Now, so this assignment that I'm about to give you is unique, not because it's on yellow paper. So in all the classes that I teach, or have taught, Chem 1, Chem 2, AP Chemistry, AP Physics 1, AP Physics 2, Honors Physics, I never, except for this, give a second assignment on the same concept. This is so important because it just kind of has to be, hey, I recognize the form, I'm off to the races. So this assignment is very similar to that one, okay? And the reason I do that, and this is literally out of every class that I teach, this is the only time I give a second assignment over the same concept. This is the only time I ever do this. So that should tell you how important this process is, okay, and the thought process. And it does have to become rote memorization. So let me hand this out. And by the way, you handed that assignment. And we've got a stapler hanging up, the new one, okay, because the other one shot crabs. And I texted the kids that installed the original one. The original one, get this, was installed in 2008. Okay, the original one that was up there was in 2008. I'm guessing that's when a lot of you were born because that was like 18 years ago. So the year you were born, the original stapler was put up there. Okay? So now we're on to the second one 18 years later. So, kind of cool. That one,